All right. Well, I hope everybody's having a good day. How was the quiz? Good? Okay. Hopefully it's not too bad. You'll have until next Friday morning if you're wanting to retake that. I'll hopefully, well, actually, by the end of today, they will be, graded and then frontline, and I'll be passing those back to you tomorrow so we can go over those again if you have any questions. Now, your next quiz is coming up on Tuesday. That's going to be a normal distribution quiz, which we wrapped up yesterday. You have a homework assignment on that currently, which is due. Okay, tomorrow, I do want to go ahead and try to stop a little bit early today to give you a little more time, just in case you do need the calculator, okay, to go ahead and definitely work on those. Oh, I already put those over here. I'll grab them for you. Who needs one? Okay, there we go. Okay. All right, but that's coming up on Tuesday. So tomorrow when we come in, we will have our next focus activity. I believe that's going to be number 5 for us. Is that right? I'd have to look, but I think so because we turned in 3, then we had 4. Okay. So focus activity, we'll talk about questions on the normal distribution homework, and then we'll just continue with this lesson right here. We're talking about correlation, so scatter plots. All right, we want to know how closely the data follows a pattern or trend. The strength of correlation is usually described as either strong, moderate, or weak, and there's a specific scale that we're going to look at here, but really when you're talking about correlation, we use the variable R. Okay, technically it can be called Pearson's correlation coefficient. You've probably seen this in Algebra 2 or some other topic. But it's a numerical value that describes how tightly packed or how far apart your data points are going to be in your grid. Okay, so the closer, the more tightly packed the points are, well, the higher this value is going to be. The closest we're going to be, we're either going to go to 1 or -1. Each of those is what we refer to as a perfect association. Do you need one as well? Okay. Those are the graphs that you normally see every day. Okay. Does anybody else need one? Okay. All right. Now, on the other end of that scale, if the points happen to be further apart, well, then you would expect a lower number, whether it's, again, a positive or a negative trend, something closer to 0 on either side. So you'll notice I've given you some examples of what could be considered strong, moderate, and weak for both a positive and a negative. Now, we're talking about the way the points are going to fall. We like to read these graphs from left to right. We always go from the smallest to the largest. So if the points seem to rise to the right, we say that's a positive correlation. Okay, and then we could go ahead and continue to describe it by strong, moderate, or weak. If the points fall to the right, well, then we say that's a negative correlation, just like, the slope of a line. Yes, sir. We need another paper. Okay. All right. Let's make sure to look for the papers when we walk in. Man, Jacob's over me. He's throwing some people under the bus. He's like, I was late and I got a paper. Okay. Does anybody else need a paper before we move on? We're good. All right. Well, the line that we draw here, that's what's called my line of best fit. Because when you're dealing with these scatter plots, and and when I say the term scatter plot, typically this is the kind of image that you think of in your mind, just a bunch of points in space. But really, any graph that you've ever come across, quadratic, radical, rational, they're all scatter plots because they're all created from ordered pairs, which are a comparison between what we know as x values and y values. It's some kind of relationship between the two. And that's really ultimately what we're trying to do here. If we have two quantities that we're comparing, well, we want to see, could there be any relationship between the two? Is there any way that one could cause the other? Okay, so this line of best fit, in mathematics, we're not very creative when it comes to naming things. If I were to go ahead and draw a line here, is there any possible way that that line would contain every point that you see? No, hence why we call it the line of best fit. We draw a line that we believe fits the data as best we can. We want to try to get as many points as we can on the line with roughly the same number of points above as we do below. We also refer to those as trend lines. Okay, so we have line of best fit. We also call them trend lines. We can also call them regression lines. or some people actually refer to them as regression curves, but all of those are used interchangeably. Okay, so trend, regression, line of best fit. Okay, and then this one here is just a little more detail, what you picked up about the correlation. You'll notice I even went ahead and provided some perfect examples of correlation here. So if we're talking linear, a perfect positive or a perfect negative, that means all the points are on the line. Okay. If we're talking about a perfect correlation quadratic, well then all the points would be on that particular one. And you'll notice typically we like to go ahead and use these with linear functions, but really just depending on the behavior of your information, the data, it could take on quadratic models, you could use exponential models, but for our purposes, we're going to be looking at linear. Okay, so slope-intercept y equals mx plus b. And just to kind of emphasize what I had a moment ago, here's the scale. Okay, so positive or negative basically tells you how the points are falling, whether it's rising to the right or falling to the right. So if a decimal value falls in either of these two regions right here, between 0 and 1 or between 0 and -1, that's going to describe to you how strong or how weak it is. So for example, the one I have up here is 0.79. Okay, so try to visualize that in your head. Would you say that 0.79 is closer to 1 or closer to 0? Definitely closer to 1. So what I'm picturing in my mind, are they going to be points that are closer together, or are they points that are further apart? Closer together. In fact, that's what R, the correlation coefficient, describes. Okay, it's going to tell me how close or far apart they are depending on the relationship between them. So the closer I get to 1, okay, the more perfect the relationship is. If I get 1, then that means it's a perfect association. Same thing on the other side. I could have a negative 0.92, which would be a very strong negative correlation. Or I could have negative 0.15, which would still be negative, but it's a very weak association. That means the points would be very far apart from each other. And in fact, you'll notice here at the bottom of these tables, is it possible that your data is just so far apart you can't even tell if it's positive or negative, and if you were to draw a line, there'd be no telling where to put the line. Okay, we call that no correlation. Sometimes two items have absolutely nothing to do with each other. Okay, but this is a very, very useful strategy for a lot of people when they're writing their IAs, especially if you have maybe some different quantities in your topic that you're discussing, and you want to see if there's any kind of relationship. All right, well, here's what we're going to do. You don't have this, but go ahead and jot this down someplace. You don't have to jot down the problem. Really, the data is what's most important here. Okay, so Sue investigates how the volume of water in a pot affects the time it takes to boil on the stove. The results are given in the table. Okay, so 1 liter of water took 3 minutes to boil. 2 took 5, 4 took 7, 5 took 9. Okay, and what we're hoping to do is find out what the correlation coefficient is. If I were to graph these ordered pairs, these XY plots, okay, well, would they be really close to each other? Would they be far apart? What kind of association do we have here? Well, there's one formula that's going to bring all this together, but the one formula is made of 3 different smaller formulas. Okay, to find the correlation coefficient R, the 3 parts, we have to find the covariance and then the standard deviation for each of the 2 data sets. So we have 2 sets of data here we're comparing. The X's, which are the liters, and then the water, which is the time it takes to boil. Excuse me. Okay, so here are the 3 formulas. You use S sub XY, that's what we call the covariance. Okay. Now, we're going to take the sum of the product of X minus its mean times Y minus its mean, all divided by N. That's the formula for the covariance. Okay, that's one of the 3 that work together to give you the correlation coefficient. Then we have the standard deviation for each of the others. We'll have the standard deviation for the X's, which is going to be this huge radical here. So in the numerator, we're again going to have the sum of the squared differences. Okay, and then we're going to have the standard deviation for the Y's. Okay, which is essentially going to be the same thing. It's just going to be altered for the Y values. The sum of the squared differences divided by N. Okay. So all three of these formulas work together to give you your correlation coefficient that we were just discussing. So R is going to be found by taking S sub xy over S sub x times S sub y. So basically that first formula is your numerator divided by a product of the other two formulas. That's how we determine the correlation coefficient. So a few of these, like always, I'm going to go ahead and show you by hand. Okay, but then hopefully that's going to make you appreciate the calculator a lot more. Okay, it's going to make you go so much faster. All right, so let's set up a table. Because if you're going to go ahead and do this, I think a table is a great way to help you out. So I'm going to need an X column. I need a Y column. Then I need an X minus its mean. Then I need a Y minus its mean. Then I need a product of the two. Now I'm running in a room, hope I can do this. Then I need, let me do the x's first. X minus x mean squared, and then y minus y mean squared. Okay. So if we're going to do this by hand, if we're going to go ahead and use the formulas ourselves, well, we need several columns to go ahead and get through all the data. And I'm just starting us with a really small one so you can kind of get the idea. Okay, so the values for x were what? 1, 2, 4, and 5? 1, 2, 4, 5. And then what were the time to boil? 3, 5, 7, 9. Okay, so let me shorten my y here. 3, 5, 7, 9. Okay. So let's go ahead and determine the mean first. All right, because we're going to need the mean pretty much in every other column that we look at. So what's the grand total of all the x's? Okay, so I'm looking for a grand total of 12 divided by the 4 items. So the x mean is 3. Okay. Now I want to do the same thing for the times to boil. So the y mean, grand total is 24 divided by the 4 values. So that's going to be 6. Okay. All right. Well, from here, it's just a matter of filling in your table and then using the results with your formulas. Okay. So x minus its mean. Okay. So 1 minus 3. Negative 2. 2 minus 3. Negative 1. 4 minus 3. 5 minus 3. Okay. Now I want to take all the y values and subtract their mean. Okay, so 3 minus 6. Negative 3. 5 minus 6. 7 minus 6. And 9 minus 6. Okay. Anybody having trouble? Anybody not sure where I'm getting the value? Okay. Well, now the next column, I got to take a product of those. So negative 2 times negative 3. That's 6. Negative 1 times negative 1. 1. 1 times 1. 2 times 3. Okay, so we're almost done. Okay. Now what I need to do is take the difference of a term and the mean squared. So we're going to take all these terms and square them. So negative 2 squared. 4. Then negative 1 squared. 1. Then 1 and 4, right? Okay. And now I want to do the same thing for the fourth column. I want to square all of those. Okay, so negative 3 squared. 9. 1, 1, 9. Okay. Now, if you go back and look at your formulas, what do I actually need to find the sum of? I need the sum of the products. I need the sum of the products. Okay. I need the sum of the square differences for the x's. And I need the sum of the square differences for the y's. So it's these last 3 columns that I need to go ahead and add up and get their totals. Okay, so what am I looking at for the products? Okay, so that's 14, right? Okay. What about the square differences for the x's? 10. And for the squared y differences? 20. Okay. So now let's go ahead and start plugging these into the formulas. Okay. The covariance S sub xy, it says I want to take the sum of those products and divide it by the number of terms. Okay, so I'm going to take the sum of that product, 14, and I'm going to divide it by 4. Now, we're not dividing by 8. Okay, we have 4 ordered pairs. We've got 4 in each set that we're comparing. Does that make sense? Okay, so this right here would just be 7/2. Okay, or if you want to change it to 3.5, perfectly fine. Okay, now let's go ahead and take a look at S sub x. This is the standard deviation for the x's. So according to this, I want the sum of the square differences divided by n. Okay, so what do we get for the sum of the square differences? 10 divided by 4. Okay, as again, we have 4 items. Okay, so we'll just go ahead and simplify it here. What is 10/4? Okay, 5/2. Or if you want to say 2.5, perfectly fine. Okay, does everybody see what I'm doing? I'm taking the formulas one at a time and using my values. I'm going to do this one last time. S sub y. So again, we have the square root. But this time I want the sum of the squared differences divided by n. Well, what do we get for that one? 20 divided by 4. Well, I'll just go ahead and write it out. What is that? 5. All 3 of these guys work together to give me r, the correlation coefficient. Remember, r is going to be found by taking S sub xy divided by the product of S sub x times S sub y. Okay. Well, for the covariance, S sub xy, we got 7/2 divided by standard deviation of the x's, we got the square root of 5/2. So I'll just go ahead and say square root of 2.5 times standard deviation of the y's, we got square root of 5. Okay. Now all we have to do is go ahead and figure out what that is. Okay. Now, before I do that, anybody not sure where I got a value from? Anybody confused? Okay. Okay, so don't worry. I mean, there is a point to this. It's a point. Okay. All right, so let me go ahead and catch up with you guys because I see a lot of people putting those in the calculator. Calculate, so I'm going to say control divide. I'm going to go ahead and just use the decimals. So 7/2 up top, that's 3.5. The square root, we had 2.5. Get out of there, times the other square root, it was just 5. Okay, so once I push enter, I should be getting my correlation coefficient. Okay. 0.9899. Wow. How would you describe that based on what we've said? Would you say that's really weak, really strong? That is very strong. That is very nearly a perfect association. So if you were to plot these points, you really should be able to almost see all of them on there. Maybe one's just slightly off, and I'm talking slightly. Okay. Now, that's how you go ahead and do it by hand. That's the big idea behind this lesson. Now, I also want you to be able to draw the line of best fit, come up with an equation for it. We call that the prediction equation. Okay, so there is a little more to talk about, but I'm going to go ahead and stop there today because that gives you right about just under 15 minutes. How many people still need the calculator for normal distribution? Okay, so I'm going to go ahead and stop early today so I can give you that time. Unless you guys just want to keep going.
Yeah.
All right. Okay.